Let's look at a special case of this electrostatic. So now that we have some general rules. So this is case one. And this case is basically parallel plate capacitors. So let's draw out the geometry. So we have a plate with an area A, and then we have a plate below this. Something like that. Oh, like that. And then the separation between these plates is D. And we want to say that the area is much larger than D. And the reason for that is uh, it's very simple to define the electric field between two plates, except at the edges. At the edges, you get the electric fields tend to bulge out, and these are called fringing fields, which you guys may have seen in parallel plate capacitors, but they're harder to deal with. So we're just saying A is much larger than D. This area is much larger than just separation, which is typically the case. And so that way we can kind of ignore the fringing fields for now. So let's just put this in a coordinate system where the distance sort of in the vertical direction, so the distance between the two plates is x in the x direction, and the plates are in the y direction. And we want to find, so we want to find the electric field, the electric flux, and the capacitance, which we know is defined as Q total over the voltage between A and B. So let's say we ground the bottom plate, and then we put the top plate at a potential V0. And so now we generally have that the Laplacian, this is a Poisson's equation, I guess. Laplacian of the potential is zero between the two plates. Because we're also assuming that this area is so volume between the plates is filled with dielectric. So there's no conduction there. So it's basically sort of a perfect dielectric. All right. So um, so let's see. So if we take the Laplacian in 2D, this is equal to, in rectangular coordinates, dv squared plus db squared dy squared is equal to 0. We're assuming A is very large. So for all purposes, in that around to the inside of the plate, the variation in y is 0. Basically, nothing's varying if you're moving. There's no change in voltage or anything as you're moving along this y direction, um, and until you get to the edges. So so for that reason, we can just say the variation y is 0, and then at x equal to 0, so here the voltage is equal to 0. and at x equal to D, voltage is equal to V0. So that's at this point here. All right, so we just have that C1 is equal to V0 over D. And V sub x is V0 over D times x. Oops. V0 over dx. Okay. So we can ask a couple of questions about this solution. Um, Basically, we're saying that the second derivative, this is a function where the second derivative respect to x ends up being zero because, basically you have a constant times x. So the first question is, question one, is this potential unique? And the answer is no, in absence of boundary conditions. We could have come up with other solutions where the double derivative is zero. But having something that satisfies Laplace's equation and the boundary conditions always gives us a unique solution. So we have to make sure that we solve both the Laplace's equation and come up with the unique solution. So that's question one. Question two is, um, can we always find a solution? Oops. So this is an existence question, and the answer is yes. We can always find a solution. So E is the divergence of V, and so that's equal to minus x hat d dx V0 over, whoops, d times x, which is minus x hat V0 over d. So again, if you look at these parallel plate capacitors, we know that in this kind of situation, the electric field is always going to be perpendicular to equipotential lines. So, this is an equipotential line. This bottom plate is an equipotential line. And then, again, the capacitance is Q over V. So, if we look at the electric flux is equal to charge density. And so epsilon times electric N1 is equal to charge density. This N1's means that it is the electric field and electric flux are both perpendicular to the plates because there's no other component. Okay, so then um, if we look at um, the area, so it's basically this area times charge density is the total charge. So here, by the way, E is basically going to be V0 over D. Oops, V0 over D. So charge density is epsilon V0 over D over V, which is, and then that's V0. So it's A, I'm going to plug that into here, epsilon V0 over D over V0. And the V0s cancel each other out, and the C total ends up being area times epsilon over D, which is indeed the capacitance of parallel plate capacitor. Okay, so that was the first example. Now let's look at another example. So let's think of our coaxial transmission line. So if you remember, this is basically our coax cable. So there's the inner conductor and an outer conductor. And let's say this is our z-axis. This inner radius is 2a, and the outer radius is 2b. Sorry, the outer diameter is 2b, inner diameter is 2a. And then what you typically do is you put your voltage on the inner conductor and you ground the outer conductor. So if I look at this at the cross section, you end up with, that's the inner conductor, and that is 2a diameter, and the outer conductor diameter is 2b, and the inside voltage is V0, outside voltage is 0. So in this case, we solve Laplace's equation. In this time in 2D. Last time we essentially did it in 1D because there's no variation in y. We just looked at, all we needed to do was to look at the variation in the x direction. So here we're going to have to look at both x and y, or in sort of radial direction. So at r is equal to a, v at r is equal to a is v0, and at r is equal to b, v at r is equal to b is equal to 0. So in this case, in this case, potential does not have um, phi or z component. So if the potential was a function of r, phi, and z, so in cylindrical coordinates, the phi and the z would be zeros because basically, again, we have a very symmetric situation. No matter what direction I look at this, it looks the same. Okay, so there's no phi or z components. So then in cylindrical coordinates, We have our Laplace's equation del squared V is equal to, so this is something we need to just look up in sort of math tables, d by dr or dv dr equal to 0. Sorry, we have to look at the solution there. So this implies that r dv over dr is a constant. Let's call it k. And so dv dr is k over r, and v of r is k natural log of r plus d, which is a general solution. Okay, so next, to make this a unique solution, we have to apply boundary conditions. And that says v of b is 0, which is k natural log of b plus d, and v at a is equal to v0. So this says that d is minus k natural log of b. So with these two, it basically gives you that k is v0 over natural log of a over b. So we end up with a vr of v0 over natural log of b over a natural log of b over r. And so this is the general solution. By the way, this is, I think, a pretty good thing to remember. Good thing to remember long term, because you're going to see this coax transmission lines all the time, coaxial cables. So when R is equal to B, B at B is indeed equal to 0. And when R is equal to A, B at A is indeed equal to V0. Okay, and then looking at the electric field is the gradient of V sub R. And so we need to find an expression for VR in cylindrical coordinate systems, which you have to kind of look up, I guess. Minus r dv over dr. It's equal to r hat v0. Oops. I think the negative goes away here, is equal to r hat v0 over r natural log of b over a in volts per meter. And then d is equal to r hat epsilon v0 r natural log of b over a, and q then on the inner conductor over a small z over small delta z distance is going to equal to the integral delta z from 0 to 2 pi epsilon v0 over a natural log of b over a times d theta, sorry, d theta, a times d theta, sorry, d phi, sorry, theta d phi delta z, and then q over delta z is equal to charge density, and it's epsilon b0 2 pi over natural log of b over a. So this capacitance per unit length ends up being over v0 is going to end up being 2 pi epsilon natural log of b over a. Again, a good thing to remember for the capacitance per unit length for coax. So these are two good examples of how you basically solve Laplace's equation with boundary conditions, and we use symmetry, integral math, and a bunch of these integral equations in rectangular coordinates, etc. Stuff that you have to look up at tables or have a pretty good math background. But fortunately, there's not that many of them, and these are just mostly examples for looking.